the paper Focus Penalizing Friendly Citations to Improve Auto Ranking, and this is work done in conjunction with David Aparicio, Pedro Ribeiro, and Fernando Silva. Just to give you an overview of this presentation, I'll start with a brief introduction about the auto ranking problem. We'll go through some of the state-of-the-art algorithms to solve this problem and their current problems and limitations. Then on the second part of this presentation, I'll start explaining our methodology. Namely, this will be divided in three main parts. One where I'll start explaining how to estimate penalties for the friendly citations. Then I'll explain one method that we use to integrate these penalties with auto ranking algorithms, and then the other method which is which presents some differences. So regarding the last part, we'll talk about some experiments that we've done. Mainly we'll start seeing that friendly citations are frequent in real world data, and we'll see that when we integrate auto-ranking algorithms, there are some gains. When we integrate auto-ranking algorithms with our strategy, it presents some positive gains. So to start, the auto-ranking problem basically consists on a task of assigning a value to an author, which in a sense that value reflects how much the author has contributed to the scientific community. These kind of values are often referred as bibliometrics, and traditionally the way that they are calculated is that they use the author's publication and the number of citations received from those authors. If you go for a lot of bibliographic databases, you'll see these indicators everywhere. For example, Google Scholar and Guide to Research used a lot each index to rank the authors that they have there. So why do we want to rank authors? Basically, there are two types of applications. One what we call the harmless application, where basically you can use the author rankings to predict who's going to win some kind of scientific prize or something like that. You can also use these rankings to see which kind of researchers our career is ascending and stuff like that. And then there are another group of applications which you call the controversial applications, where basically you can use the author ranking to assign research grants, to decide who's going to be part of scientific community, or even to promote someone within an institution. And we have to keep in mind that for this group, these are important decisions, and usually what is done is that they require some human intervention. However, still humans look at indicators such as bibliometrics to make this decision. So with respect to the state-of-the-art algorithms for auto-ranking, basically they could be divided into groups. On one side we have the citation count, which basically just looks into the raw number of citations coming from the publications, and on the other hand you have the citations network analysis, where basically you create a network that represents citation relations, and these networks could be either a paper citation network where papers have relations to the papers that they cite, and also you can have the author citation network where basically you have authors that cite each other, and in this kind of networks you have a lot of metadata associated with the links, and the metadata could be things like the venue of the citation, the year, and stuff like that. So to give you some more difference about these two methods, on citations count you have things that are very common such as h-index, the g-index, and the raw number of citations that should be used everywhere. And the main advantages of these algorithms is that they are easy to estimate, they are easy to interpret, and also they are computationally inexpensive, and they have been the standard for several years. However, they have a very significant problem, and this is that they ignore the citation relations, which is a problem. Because they only give credit to direct citations. On the other hand, we have citation network analysis, where basically the algorithms give credit for indirect citations. If an author A cites an author B and that B has cited C previously, C is going to get some credit from the A citation. And also another benefit that they have is that they measure impact at the group scale, and by that I mean that for the citations count, it doesn't matter who cites you as long as they cite you, while on the citation network analysis it is more important to being cited by other important authors. The one drawback of the citation network analysis algorithms is that they require a lot of more computational power, and also they require a lot more data, because for the citation counts you only need the number of citations. On the other hand, for citation network analysis you need the relation who cites who. So independent of the auto-ranking algorithm to use, one problem that has been identified in the literature is the citation boosting, and basically this consists on the on the practice of increasing the number of citations of an author to undeservedly increase his scientific impact. This has been studied a lot in literature and has been identified as a problem. Throughout the literature, there are three patterns of citations that have been identified as mostly used for citation boosting. The first one is the self-citations, where they are quite self-explanatory, where basically an author cites himself multiple times. Also, there are co-author citations, where basically you are preferring to cite your co-authors than on any other authors on the community. And then there are reciprocal citations, where basically two authors or a group of authors interchange citations among each other throughout the time. So just to keep this clear, it is expected that these kind of citation patterns occur naturally because it is normal to cite your previous work. It is also normal to cite your co-authors, or you even change citations in other authors if you are work on similar areas. However, this problem, the abuse of this kind of patterns has been identified in literature, and there are multiple papers that document this, that they could lead to unrealistic author rankings. So it kind of becomes important to mitigate the effect of these citations when you want to estimate scientific impact. Another thing to keep in mind here is that the state-of-the-art algorithms for author ranking, at most what they do is that they only deal with self-citations, and they just remove them, and they do not handle co-author or reciprocal citation, which is a problem for the author ranking problem. So here comes our part of the contribution in our work. Basically, our main goal is to propose a framework for author ranking algorithms that decreases the impact of citations that result from citation boosting patterns. The idea is that by doing that, we are going to create a more fair rank, and obviously it will help the author ranking task. So our initial effort is this work, and on this initial work, we are going to propose a friends-only citation analyzer, which is a acronym for FOCAS. And here we're only focused on applying this to citation network analysis algorithms, and also we're only focusing on friendly citations, which is defined as the group of self and co-author citations. So just to be clear, in this work you are not going to address reciprocal citations, and only address the two previous groups that I just mentioned. So before I start explaining our methodology, I'll give a brief introduction about the author ranking algorithms that are applied on citation network analysis. And more detail, I'll be focusing on author level author ranking algorithms, which basically means that the citation network consists of authors. So the idea of these algorithms is that they are mostly based on page rank. So they have two steps. They have one step where they initialize the score for each author, which is called the score initialization. And then after defining this initial score, we have the score diffusion step, where using the network we start diffusing those scores until they reach convergence. This is typically done in a page rank function. So there are a lot of algorithms that have been proposed in literature for this task, and the main difference between them is that they use different strategies to define the initial score of the authors, and also they use different strategies to define the weights on the network. For example, some algorithms assign higher importance for citations coming from more prestigious venues, others assign more importance to more recent citations, and stuff like that. So there are a lot of options here. But the main point is that on the end, after defining the initial score, they have a kind of network like this, where you have links between the authors and weights associated to each link. So based on this kind of information for the author ranking algorithms, what we propose here is that we are going to look also not only at the citation network, but also into the co-authorship network. And we're going to do is that for each citation coming on a citation network, as you can see here, we are going to propose a penalty P, and this penalty P is based on the relations between the two authors in the co-authorship network. So the idea is that the higher the penalty P is, it means that somehow the authors are more related in the co-authorship network, and then the higher the value of the P, and then the less important the citation will become in the citation network with respect to author ranking. So I'll start now explaining how we estimate these penalties based on the co-authorship network, and basically we define three criterion, and we have to keep in mind that this is each of these criteria is applied for a citation, and a citation consists of something like that's author A citing author B. So for the distance criteria, what we do is that we look into the co-authorship network and see which is the distance between the authors A and B, and the more closer they are, then the higher the penalty is. So if B is a co-author of A, it is going to be a higher penalty that if A co-authors with C and C co-authors with B, and so on. So for the frequency criteria, what we do is that we estimate the number of times that A and B collaborated, and the more times that they are collaborated, the higher the penalty is. And finally, for the recency, what we have is that the more recent the collaboration between A and B is, the higher the penalty is. So based on this, we define these three base criterion, and also we can make combinations between these criteria. For example, we can combine the criteria of distance and frequency and create what you call the DF criterion. We basically combine these two. We can also have this for the frequency and recency, for distance, frequency, and recency, and so on. So basically, we can create all these kind of combinations, which give us a total of 7 different criteria that we can use. So another thing to highlight here, and I'm moving quite fast on this part, and if you are interested in this, I advise you to look into the paper, because there we have some example of these calculations, and I think it would be easier to understand. But another important thing to highlight here is that the penalties are estimated only consider collaboration prior to the citation, and by that I mean that each citation has a here, and so if A cites B and they don't have any previous collaboration, then there's no penalty for the citation. But then if they start to collaborate and then in the future B cites A, or the other way around, then they'll have some penalty, because in the meantime they started collaborated. So the point is that between the two authors, you can have different penalties associated between citations between them if the citations happen in different years. So now that we've seen all the estimated penalties, we'll see the first strategy that implemented how would we integrate these penalties with the author ranking algorithms. And the way that we do that is the first strategy is called FOCAS-NAIVE, and what we do is that directly we apply the penalties to the citations weights in a pre-processing step, and basically it decreases the weight associated to citations coming from friendly citations. So if you look at the sample of this image here, if you have an author that's at some point has a score of 0.28 in the score diffusion step, and if equally cites two authors with the same weight, then he's going to divide the score equally between them. And if there are no penalties, they still receive, each one receives the same score. But if in a pre-processing step we apply the penalty of 0.5 to a citation, then it's going to decrease, and then we'll see that we'll start decreasing the score given to the specific author. And as a result, since it's a page rank based algorithm, you always have to send all the score of an author to all the author that he cites, and he's going to increase the score received for the other author. So this is kind of a effect that you want to achieve. On one hand, you are decreasing the score received from authors that use different citations, and also as a consequence, you are also increasing the score of authors not being cited by friendly citations. So this is kind of thing that we want to achieve. Another point to highlight here is that this algorithm does not require changing the author ranking algorithm. The only thing that it does is that after the author ranking algorithm defines the citation weights, you apply the FOCAS-NAIVE strategy, and then you can proceed with the author ranking algorithm to the score diffusion step until it reaches convergence. However, there is a big limitation of this approach, and this limitation is that it fails to penalize authors when the citing author only cites other authors through friendly citations. So I know this is kind of confusing, but let's take a look at this image here. So on the left, you have the same scenario, and without penalties, they all receive the same score. But then if you apply the FOCAS-NAIVE, and for some reason the penalty determined for both citations is 0.5, then you are equally decreasing both links, which means that in the end, the authors will still receive the same score from this author, which basically means that the FOCAS-NAIVE did not have an effect on this on this specific case. So this becomes a problem. So in order to overcome this limitation, what we did is that we proposed FOCAS. And what does FOCAS instead of applying direct to the weights of the citation network, it lets the score diffusion step takes proceeding with the normal weights, and then after the score is received for the authors, it decreases the score of the authors depending on the penalty that was applied for that link. So I know this might again might sound confusing because I don't have too much time to go into the details, but let's take a look at this image. So we have the same scenario as here, and this time we have the same penalty applied to both citations. This time we are going to let the score diffusion step spread the score normally, as if there isn't any penalty applied to the citation. And then after each author receives this score, we are going to apply the penalty and decrease the score of an author. What basically it does, what this does is that it is decreasing the score of half because the penalty is 0.5. So we are removing 0.2 score from each author, and then what you do is to reach convergence and maintain the stability of the whole page rank based approach. We are going to save this score in a kind of sum of it in a variable, which in this case it totals 0.4, as this is 0.2 from the two authors, and then the total sum of penalized score at that round is divided according to the initialization vector defined by the author ranking algorithm. So I'm sorry, I don't have time to go into too much details about this approach. If you are interested in this, I advise you to read the paper, which I think you'll have much more details to explain this. But the main point here is that this time the FOCAS operates at each iteration of the author ranking algorithm, and so as a result, it requires kind of change the author ranking algorithm, which can be a disadvantage. But as you will see in the experiments, the results are far better. So moving into the experiments part, what we did to see if our strategies were proved to be any good is that we created a data set from the WLP database. We selected the 7 top tier conferences from computer science. They have the names there, and basically this gave us a network. 2 networks: the co-authorship network and the citation network, consisting each one of around 28,000 authors. And for the citation, we have 5.7 million relations, and that means that an author cites another author. And for the co-authorship, we have 0.15 million, which means that an author has collaborated with another author in a specific paper. So besides the network, we also need some kind of ground truth ranking to validate our results. And what we did is that we used the best paper award information from these networks as the ground truth. And the idea is that we want to rank higher authors that have received the most best paper awards. So just keep in mind that the point here on this test is not to define the best author ranking strategy, because this is not the point of FOCAS. And instead, FOCAS what aims to do is that it takes the score of the author ranking algorithms and it wants to improve them by limiting the impact of random citations. So what we do is that we measure the baseline of each of 8 author ranking algorithms without any implementations, and then we measure its performance after applying FOCAS to it and see the gains that we obtain. So the first thing that we measure on the data is that see how often random citations occur on a real world data. As you can see here, I don't have too much details to go into this table, but basically I'll only address the columns, where basically the columns L0 means that there is the columns reflect how far in the co-authorship network the citations come from, and L0 means that is a self-citation, and L1 it means that the citation comes from one direct collaborator, L2 means that that has been a citation coming from a co-author of your co-authors, and so on. So if you look into the whole network, you can see that most of citations come from a list of 2, but there is also a significant value of citations coming directly from your co-authors. For the other roles, what we did is that we kind of restrict the network to only authors that have won best paper awards, and this is what you get on the third row, and then only the top 100 authors from the citations that from the best paper awards, and so on and so on. As you can see here, there is a clear distinction between where the citations come from, where you consider only authors that have won best paper awards, and the whole network. So this kind of gives us motivation that maybe the best authors in this network are not using so many close relations citations in the co-authorship network as the whole network itself. So with respect to the experiments, the first thing that we did is that to measure the baseline. Basically, we compare the ranking produced by the author rank algorithms with the ideal rank from the ground truth, and we have this baseline score for each algorithm. And also, since removing self-citation is a common practice on literature with author ranking, what it did is that to measure the gain of removing self-citations from this method. This only removed self-citations from the network, and you can see the gain, and you can see that on average the gain is very insignificant, is 1.4 for all the 8 methods that we tested. So after that, we compared adding these algorithms, the gains of algorithms when we had the FOCAS-NAIVE approach, and we added the FOCAS-NAIVE with 7 different criteria. And again, I don't have too much time to go into these details, but you can see that we have some consistent gains in most algorithms. Still, for some approaches, the gains are not very significant. And and overall, in the best case scenario, the best criteria was the distance, and only presented an average gain of 13.2% across all the methods, which is not that bad, but is also not very significant, because it also was not consistent. For example, for the RLPR algorithm and SKIAS and SARA, it didn't prove any positive gains, which was not ideal. So now we move to the comparison with the FOCAS algorithm. And here in the FOCAS, you can see you apply the same criteria. We tested the 7 different criteria for all the methods, and you can see here that the gains are more significant, which basically means that the limitation of the FOCAS-NAIVE was real. And when we overcome this limitation, we are able to improve the results significantly. And still, for the criteria, distance was the best one. And and you can see here consistently and significantly improved the gains of the author ranking algorithms. So just to give you a conclusion about this work, so basically we observed that auto-rank algorithms lack strategies to deal with authors that boost their own scientific impact by using citation boosting patterns. We also propose FOCAS, which is a method that penalizes friend citations and has a total of 7 different criteria for citation penalty estimation and 2 different strategies to apply these penalties. One is FOCAS-NAIVE, where you can use it as a pre-computation step that changes the network weights before the auto-rank algorithm processes the diffusion steps part of the algorithm. And the other one is FOCAS, where basically it operates at each iteration of the auto-ranking algorithm and basically modifies the score received from friend citations. So in the end, we observed that FOCAS is capable of improving the state-of-the-art algorithms by an average of 25%, and in the best case scenario, we're able to improve to present a gain of 46% in a real-world network consisting of 7 top-tier conferences in computer science. So just to give you some ideas of our future work, as I said, this is our initial effort to tackle this problem. So basically we want to study if this kind of results is consistent with another real-world citation networks. And more specifically, we want to test if the results that we observe for the computer science also applies for different research areas. Also with respect to FOCAS, we want to make an adaptation, because right now we are penalizing every friendly citation, which may be not ideal because, as I said, they are naturally occurring in the community. But in this time, in this adaptation, what we want to do is that we aim to only penalize the excessive use of these citations, and this is something that we are looking into. And basically the third strategy and the third point in the future work is that we want to implement some kind of strategies to deal with reciprocated citations, which is something that we currently not do. So thank you for your time. Please, if you have any questions, forward them to the email that you see here, and thank you.